What if the most fundamental assumption in machine learning, that we must train models through iterative optimization, is actually unnecessary? This dissertation reveals a different path, constructing predictive models directly from data using explicit mathematical formulas, no training required. To understand why this matters, we first need to examine what's broken in the current paradigm. Building on that concern, the authors identify 4 fundamental limitations of empirical risk minimization. Standard approaches rely on universal approximation theorems that are existential, meaning they prove solutions exist without showing how to construct them. Meanwhile, iterative optimization faces serious practical challenges in high dimensions, and global loss functions can't capture the local geometric structure that matters for real-world data. The alternative is to build approximations constructively, respecting the geometry hidden in data. Here's the key innovation. Instead of training, the method projects data from an unknown manifold onto a sphere, then constructs an explicit kernel interpolant using highly localized spherical harmonics. The error bound depends only on the manifold dimension and local smoothness, achieving optimal rates without any optimization or tangent space estimation. This comparison reveals something striking about the constructive approach. While global error metrics might look similar across methods, the new technique concentrates errors precisely at function singularities, producing dramatically better percentile performance. The radial basis function errors, scaled down by a factor of 1,000 here, show the method's advantage isn't just theoretical. The constructive paradigm extends naturally to transfer learning, reframed as geometric lifting. Traditional transfer learning uses empirical tricks to align features, but this work formalizes transfer as explicit lifting through joint spectral geometry. The framework precisely specifies which regions of the target space can be reliably predicted from limited source data, and it quantifies how source smoothness translates to target smoothness based on the geometric compatibility between spaces. Perhaps most radically, the work reconceives classification not as function approximation but as density geometry. The mask algorithm treats classification as partitioning a mixture measure into its component supports. By performing multi-scale density estimation with localized kernels, it discovers natural clusters without assuming disjoint class supports. Active querying then labels only the minimal set of representative points needed to characterize each cluster, extending labels via nearest neighbors. These results on hyperspectral image classification demonstrate the practical power of the support estimation approach. Mask matches or exceeds the accuracy of established active learning methods while using substantially fewer labeled examples. The advantage grows as the labeling budget tightens, exactly the regime where efficient learning matters most. This dissertation fundamentally inverts the relationship between approximation theory and machine learning, proving that for broad classes of problems, explicit construction can replace iterative training entirely. To explore the full mathematical framework and its implications for building more efficient and interpretable learning systems, visit emergentmind.com.